prove a theorem is a logic argument that establishes the truth of a theorem. It consists in a sequence of steps. Each step has one or more reasons that justify its validity. There are four main types of proof methods. Those are direct proof, contrapositive proof, contradiction proof, and counterexample. The most natural way to prove a theorem, if it is a conditional proposition, is direct proof. If we want to prove a proposition P then Q, it's enough to prove that Q is true whenever P is true too. Direct proof of P then Q, we assume that the hypothesis P is true, and we prove by using logical argument that the thesis Q is true too. If x is an odd integer, then x to the 2 is an odd integer. Proof: an odd integer is defined by x equal to 2a plus 1. So, in consequence, x to the 2 is odd. The proof by contrapositive uses to prove theorems and propositions that have the conditional form P then Q. In this way, if we want to demonstrate P then Q by contrapositive, it is enough to demonstrate no Q then no P. We assume that no Q is true, show that if no P is true. If 3x minus 1 is even, then x is odd. Proof: suppose that x is not odd, then x is even. X is defined by x equal to 2a. In consequence, 3x minus 1 is odd. A contradiction proof of a proposition P by assuming that P is false. That is, that no P is true, and ends by deducing that for a certain proposition C, we have that C and no C is true. That is a contradiction because a proposition and its negation cannot have the same truth value. So to prove P by contradiction is enough to show no P, then C and no C. If x to the 2 is even, then x is even. Proof: suppose x to the 2 is even and x is not even. That is, x is odd. X is defined by 2a plus 1. So in consequence, x to the 2 is odd. We have found a contradiction. X to the 2 is even and x to the 2 is odd. In a biconditional proposition, both P and Q must have the same truth value for the proposition to be true. In the proof of a biconditional proposition by counterexample, we seek to obtain a case when P and Q don't share the same truth value, because this proves that the proposition is false. Any number divisible by 10 is also divisible by 2 and 3 too. Proof: if the given proposition is true or false. P if and only if Q. When the number is not integer divisible by 10, 2 and 3, we will found the counterexample.